Lesson 110, Mathematical Modeling. Mathematical modeling is finding a function to fit data points. So it's going backwards. So instead of having the function and you get the points and you make graphs or whatever, going the other way. We have our graph for our points. We're going to get our function. For doing linear, we use what's called the least square regression. And that gives the best fitting line. Now in real life, the points don't line up in a perfect line. In real life, you'll get data points that hopefully give you some sort of linear relationship, but won't be exactly straight line. The amount of error between the perfect line and the best fitting line is called the correlation coefficient, or R. If it's a perfectly straight line with a positive slope, it's +1 or close to that. Correlation coefficient is between -1 and +1. And you can see as it gets spread out, it goes closer and closer to 0. At 0, there is no correlation. There's no relationship between the x and the y. As the slope goes down, the correlation coefficients are negative. We get a negative slope when it means a negative correlation coefficient. So if it's closer to 1 or -1, the better the line it is, the better the relationship. Closer to 0, the worse the relationship between them is. Let's try an example. The number in thousands of female Air Force personnel on active duty for these years is given in the table, with T0 being 2,000. So we're going to say this is T, this will be 0, 1, 2, 3, 4, just to be convenient, smaller numbers. Well, they could do this by hand, by plotting the points and drawing the best fitting line and finding the equation of the line, or we could use technology. On a TI graphing calculator, you'd hit Stat, select Edit, and put your data in. Then you hit Stat, go over to Calc, and down to Linear Regression, hit Enter a few times, and that should give it to you, unless your settings are messed up. I'm going to show this on the NumWorks calculator. So on the NumWorks, we're going to go to Regression in the home screen. Then we're going to enter the data into the data spaces. All right, and then if I go up to the top and over to Graph, you can see the points. If you'd like to see a line on it, you could hit Enter and pick Linear. And that gives you the best fitting line. If you'd like to see the equation of the line, go up and over to here where it says Regression, and you can pick your model, and there is the regression. So you can see it's y equals 1.99x plus 66.66. So in this case, the personnel would be 1.99, be t instead of x in our case. And from that, we could predict how many female personnel would be in the Air Force in some future years. In real-life problems, this is done sometimes, and it's often used to find rate of change. How quickly is the number of Air Force personnel changing, or something like that? And the slope of the line is your rate of change. So that's usually what we're looking at as the most important. How quickly is it changing? Other important thing is what extent is our model useful for? So let's say we have these points and we have this line through there. Interpolation is within the data, and it usually has small errors. So it's inside the data points. You can assume that anything that you get from there is going to be close to what it really is. Extrapolation, however, is outside of the data. The further you get away from your data, the more of a guess it is. For example, we tried modeling the Air Force, female Air Force personnel with a line. But what if something happens and suddenly females aren't allowed in anymore? Or something happens and maybe the Air Force just increases the number of recruits over across the board, but still we have more females. If you go backwards, females weren't allowed in. So that is extrapolation. It's outside of the data. Could have huge errors because you don't know the conditions. The model might not fit. The last type of mathematical modeling we'll look at is variations. We have three types of variations. There's direct variation. It's modeled by y equals ax. And it's direct because if x goes up, the y goes up. Go the same way. Whatever happens to the x directly happens to the y. Inverse variation, modeled by y equals a divided by x. And here, if x goes up, the y goes down. The opposite thing happens. And then we have joint variation, which are several different variables that are multiplied together. So the z in this case would depend on both x and y. Notice they all have this a. That a is called the constant of variation. If you're reading a problem and it says it varies, that varies indicates you're going to put a equals a. So a company found the demand for its product varies. All right, what varies? The demand varies. So D equals A. Inversely, okay, so we're dividing as the price of the product. Okay, so demand, D, varies, equals A, inversely, divided by price. So now when the price is $2.75, so I could put that in for the price. The demand is 600 units. Write an equation. All right, so I could multiply and I could find A. So multiply both sides by 2.75. And we get 1,650 for A. So our equation would be D equals 1,650 divided by the price. And then you could put in any price and find the demand.